So welcome back. The first speaker of this afternoon session is John Hauenstein. So he is started working at the University of Notre Dame. He's going to talk about solving polynomials. So this is the first lecture of two.
So thank you, Hiro, and I want to thank the organizers for the invitation, not just for this talk, but to be here the whole semester. So before I start, there's a workshop. The second workshop is on solving polynomial equations. So this is jointly organized with Frank Sotile and then Pascal Courant. So we'll bring in lots of good speakers to tell you more about solving polynomial equations and their applications as well, the complexity of them. So for my first talk, many of you might be familiar with symbolic methods. So I want to sort of give you a quick my interpretation of symbolic methods, and then also sort of tell you the basic idea of numerical methods. And then the rest of my talk will try and answer the question, what does solve mean? And then my next lecture on Thursday, I'll actually go into more details about numerical algebraic geometry and how do you actually solve things. Okay, so from a symbolic standpoint, you can think of, say, Grosvenor basis or resultants, eliminants, etc. And what you want to do is you want to take your system of equations. So you have a given system of equations, system of polynomial equations. Let's say f1 of x1 through xn is equal to 0 through fn x1 through xn equal to 0. And what do these methods do? All of the symbolic manipulations is they manipulate the polynomials or I will say deform to produce new sets of equations. New equations which are easier to solve. So we've been doing this in linear algebra for a long time, so let's write down a linear system of equations. So we have x minus 9y plus 8z is equal to 5. 2x minus 3y minus z is equal to minus 5. X plus 3y minus 2z is equal to 2. In 1 second, can anyone tell me what the solution is? No. Okay, good. Suppose I did some manipulation. And if my math is correct, these two sets of equations define the same solution. And hopefully from the second one, you're able to actually see how to find the solution. Z is equal to 5 halves. Plug that into here. Compute y. Plug y and z into here and compute x. So these two sets of equations define the same solution, but one of them is much easier to solve than the other one. So this is the basic idea of, say, Grosvenor basis. Is here you have these so-called pivots in linear algebra, and pivots are replaced with leading terms or the leading monomials of algebraic equations. So you turn a system of equations which, say, is dense into something which has sort of nice pivots, and that way you can easily answer your question. So this is how I see symbolic methods. It's turning your system of equations into an easier system that you can now quickly solve. All right. Let's move on to sort of numerical. So the basic thing of numerical algebraic geometry, the basic tool is homotopy continuation. And the idea is you want to solve f of x equal to 0 by first solving a new system, g of x equal to 0. There's a lot of art involved with choosing this new system g, and we'll talk about some of the foundational ideas behind that throughout the 2 lectures. The system you give me is too hard to solve. So I'm going to ignore your system and solve my own system. That's easy to solve. So for instance, suppose my f of x is x squared plus 3x minus 5 and 2xy plus y squared minus 3x plus 2. For instance. You might see an idea of how to solve this. The first one's quadratic, and one variable. You can find the solutions, plug it in, and get the y's. Compare that with this system. G of xy is x squared minus 1, y squared minus 1. You should be able to immediately solve g. And now what we want to do is use the solutions from g to give us the solutions to f. That's the whole idea of this. So we're going to set up a homotopy. And for simplicity, let's just take a linear interpolation. F of x times 1 minus t plus t times g of x. And we want this to be equal to 0. So this defines a system of equations. And for simplicity, let's assume here that f is f1 through fn, and x is x1 through xn, where these are the same size. So I have the same number of equations as I have variables. So I have a well-constrained system. And now let's assume that g of x equal to 0 has d solutions with the determinant of the Jacobian of g not 0 at each x star such that g of x star is 0. So no,
Not 0.
not 0. I said not 0 and didn't write it. Very good, thank you. So these are called the non-singular solutions. So assume that all of the solutions are non-singular. This is a system of equations of n plus 1 in n plus 1 variables. There's n x's and 1 t. And n equations in n plus 1 variables. So you would hope this defines a curve. And almost everywhere it does. And let me tell you what I mean by that. So what you should think about is your t here is a complex number. And what happens at t equal to 1? So let's plug t equal to 1 in here. 1 minus 1 is 0. So my f term vanishes. And I have 1 times g is equal to 0. So essentially I have g equal to 0. At g equal to 0, I have d solutions. Everything is non-singular. So think back to analysis. We have the implicit function theorem. Tells us that locally nearby, my solutions can actually continue as I change t. So the implicit function theorem says that for t near 1, solution has x sub t of h exist and are smooth. A solution of g equal to 0. So at every point of g equal to 0, I know that there's a solution path passing through there. So as I vary t, I get these nice curves. And what you can show is except for finitely many values of t, this is always true. So move from analysis, local analysis, to algebraic geometry. And except for finitely many t star, we have exactly d solutions, all non-singular, to h of x t star equal to 0. So now the art is we want to get to 0. We started at t equal to 1. We want to get to 0. We don't know if the path along 0 to 1 is actually good. And many times it's not, because the real numbers have some interesting properties. So many times I'm going to have some of these t stars lying here. But I know that there's only finitely many things. And over the real numbers, this is a two-dimensional set. The complex numbers are two-dimensional. And so that means I can draw an arc that misses these points. And that's going to be my deformation. I'm going to deform along an arc that misses these points. How do you construct such an arc? Well, that's a probability 1 statement. And so let me tell you sort of the whole idea.
How do you know you're on a bad arc?
Very good. How do you know you're on a bad arc? You have less than these solutions or one of them is singular.
You only know it when you're
You only know it
After the fact.
Yes.
Okay.
Yes. And this is exactly where the probabilistic methods of numerical algebraic geometry. And so what I mean by that is methods work except on a Zariski closed proper subset.
You don't know to prove that if you get correct solution.
Yes, that's correct. A priori, I don't know how to prove I have the correct solution. But if I have the wrong solution, then I can verify that I have a singularity.
How do you know how many solutions you have?
Because I choose my G, and because I've chosen G, I know I have that many solutions. Think back to x squared minus 1, y squared minus 1. That has 4 solutions.
Yes, but how you verify for some concrete point how many solutions you have?
You just have to exhibit them.
You can.
Yes, just write them down. Yes.
Are we looking at real solutions only, or any?
This talk is over complex numbers. I'll leave Cynthia to maybe talk about some kind of aspects of real algebraic geometry, but I will mention about real numbers very briefly in my second talk, if Cynthia doesn't say anything. Okay, good. So what you move from in the symbolic case, you can prove that every computation you do was correct. You can prove that if you subtract 2 integers, you get another integer, and all of your computations in your Grosvenor basis are correct. Whereas numerical methods, we rely upon the probabilistic nature of Zariski closed sets. They're small. The probability that a random point lies on a given Zariski set based on your probability distribution is probability 0. So the methods work with probability 1. By switching from always correct provable results to probability 1 results, the idea is now that we can solve much bigger polynomial systems. And once you know the answer afterwards, you can then go back and prove using your favorite tools that what the method gave you was correct. And there's several people in the audience who have used numerical methods to find the answer and then gone back with some other technique and actually proved that that answer was correct.
Just one more quick heuristic question. Does the structure of the singular points give us some heuristic knowledge on how to design good Gs?
Yes, yes. So I'll get into this very briefly. But because you're given F, you can look at its structure. What are the degrees of it? What are the monomials that appear in it? What kinds of things should happen at infinity? That will lead you to design G to match this. And there's an art to this. I won't be able to say much of it, but I'll lead you there in a little bit. Okay, so that's my introduction to the difference between symbolic and numerics. Because you have a solution like this, you know that x sub t is analytic with h of x sub t equivalently equal to 0. And so what we've done is you can turn this into a path tracking. This defines a curve parameterized by t. And so you've turned algebraic geometry into a differential equation solver. And so let me tell you that. This is what's called the Davydenko differential equation. We start at a known solution of g equal to 0, and then we adjust with respect to t based on the Jacobian times the system. So you immediately see from this differential equation, my Jacobian has to be full rank in order for it to be invertible. So here's where I'm going to see if I run into problems. So we've turned solving polynomial systems, f of x equal to 0, into solving differential equations. And then use your favorite differential equation solver to come back to find the solution. Okay, good. Questions so far? So that's my brief introduction to comparing symbolic to numeric. Now let's move on to what we mean by solve.
Actually, maybe
Yes?
you could just give a little history as to when these homotopy methods started being
Ah.
used.
So the history is quite interesting in that homotopy methods have been used, they predate computers. Homotopy methods have been used since sort of the late 19th century for solving PDEs. And so PDE and ODE people have been using sort of homotopy methods to solve their methods, at least from a theoretically rigorous standpoint. Davydenko differential equation. So before, people were thinking of these paths using topology. And Davydenko in the 1950s had this idea, instead of using topology, let's use differential equations and come back to it. And this was about in the mid-50s, and then throughout the 60s and 70s, and then sort of exploding in the 80s, 90s, and 2000s is sort of when homotopy methods sort of really took off in the algebraic geometry context.
I think the first people to do it came from a mechanism designed robotics.
Yes, yes, exactly. So mechanical engineers have been using these to design mechanisms since the late 50s, early 60s in the very basic first computers. So the long computational history has been there, as well as the theory from the late 1800s. Okay, good?
Does this method can work for any kind of equations, or there is like limitations for what kind of equations can be used?
So as I wrote down the homotopy, it works for square systems, where the number of equations is equal to the number of variables. You can always, it depends upon what you mean by solve, and that's what the next whatever length of time I have left, is what do you mean by computing the solutions? Do you mean computing some components? Do you mean finding isolated points of an overdetermined system? But every problem can be reduced down into exactly what I told you. You have a square system of polynomial equations. It takes some tricks to get it there, but it mainly depends upon the person asking the right question. What kind of solutions to this system are you looking for? Okay, so let's move on to solve. So when you ask your favorite program to solve this system, what are you asking it to do? That's sort of the fundamental problem here, is trying to find out what you're looking for so that the software can give you the answer you're looking for. So let's think back to classical times. So, yes?
Sorry, one final intro.
Yeah, absolutely.
Up till this point, have you anywhere used the fact that we are dealing with polynomials, or it's immaterial so far?
What I've used is that there's finitely many solutions at the end, finitely many isolated points. Everything here, this whole deformation works with any kind of analytic function. And so you can do homotopic continuation over analytics. You just can't prove that you have all of the solutions. To get sort of the methods to prove that you find everything you want, you have to use algebraic geometry.
But also, if you have finitely many dead points, I mean, somehow
Yes.
that should rely on polynomials, right?
In some extent, yes, it does. Yeah, thanks, Greg. Okay, so let's think back to the ancient period. Say Egyptians. Solve meant to sort of write formulas in terms of the coefficients. So I hope everyone can answer the first two, right? So x here is minus b over a. I'm assuming this is linear, which means a is non-zero throughout the talk. The next one, I hope everyone has gone through high school algebra. Good. X is minus b plus or minus b squared minus 4ac all over 2a. Anyone know the cubic formula?
It's very complicated when you have that many coefficients. Yes.
Use enough space.
Yes.
What about the quartic formula? Has anyone ever looked at the quartic formula? Okay, a few people. Good. And then what happens? So Abel Ruffini in roughly 1830s, no formula.
No, there's no algebraic formula. There's
Yes.
an analytic.
Yes.
Of course. No formula with radicals.
No formula involving plus, minus, times, divide, radical, such that to solve general quintics, etc. Very good. Okay, so I look at this and say 300 years ago, they predicted that computers were going to take over algebraic geometry. This shows that we need computers to help us. We need numerics to approximate our solutions. We need computers to refine, to reinterpret our polynomials. So, sort of 300-year-old math theory together with modern computers sort of have led to this computational algebraic geometric sort of revival. That's my my pitch for that. Okay. Good? So we can't write general formulas down, but what we can try to do is maybe solve means to compute a solution. So I give you a system f of x equal to 0, and I ask, does there exist a solution, or is there no solution? Okay, so let's say the univariate case. Univariate case. I give you a univariate polynomial degree d. Does there exist a solution? Yes. Fundamental theorem of algebra. Good. So if a univariate polynomial of degree d has d roots, counting multiplicity. So univariate polynomials, and this was used in the previous talk, we always know solutions exist. What about positive dimensional things? And this is Hilbert's Weak-Nostalensatz. And it says that if f, which is again f1 through fn, equal to 0, has no solutions, if and only if there exists g1 through gn, such that I can write 1 as f1 times g1 plus f times gn. Okay? So how is this useful? In particular, how is this useful to what we're studying this semester? Let's look at 3 by 3 matrix multiplication. So pick your favorite R and look at the system. I equal 1 to R of A I JK times B I L M times C I N O minus K times L M times N. Let's erase Kronecker deltas of these M, N, and OJ. And here I loop over all J, K, L, M, N, and O from 1 to 3.
So I'm not sure I understand the notation.
Okay? So you pick J, K, L, and M, O in 1 to 3, and I'm going to write down this polynomial. Okay? So I have 729 polynomials. I have 6 choices here and 3 to the 6th.
So
What is A, B, and C?
yeah, you got it. So the A, I, J, K are variables.
Yes, A, B, C are variables which live in CR cross 3 cross 3. Variables, indeterminates. Okay?
And O is an index.
Index,
not a
okay, maybe
zero.
I should change it to P.
Yeah, and it'd probably be better if I were Greek or something, because it's a completely different type of index.
Okay. All right. Okay,
Just aesthetics,
yes.
but a lot of that is aesthetics.
So these have a name. These are called the Brent polynomials. And what's known about them? When R is less than or equal to 18, f of R equal to 0 has no solutions.
Why are these called Brent polynomials?
Because there was a paper of Brent, which were the first ones to write them down. And if you read Lauterman's paper, he refers to this paper of Brent. Good. So that means whenever R is less than or equal to 18, I can find a linear combination of, or a polynomial combination in my ideal so that 1 is in there. Okay? What's also known? If R is greater than or equal to 23, f of R equal to 0. So this was, I guess, Lauder. F of R equal to 0 has solutions. And the first one to show this was Lauterman for 23. And so between 19, and 22, it's unknown. So you can answer questions about complexity of 3 by 3 matrix multiplication just by trying to exhibit or prove that no solutions exist. So we don't care about all solutions. We just want to know, does there exist any solutions?
So what's the relationship to this matrix multiplication?
If you have a solution, then these tell you exactly how to do the matrix multiplication.
I think this expresses, I was confused first, but this expresses that the tensor of 3 by 3 matrix multiplication
Yeah.
has rank at most R.
Yeah,
It's the
exactly. This
representation.
corresponds to the tensor of matrix multiplication, and this corresponds to a general tensor of rank R,
Okay.
and it's showing that the rank of this tensor is at
Just the
most R.
choice of indices is a bit unusual, but
Yeah.
Okay, sure, okay.
Okay. Yeah. Okay, good. Thanks, Baron.
Depends on how much coffee you've had.
explicit. Yes, it's explicit.
As clear as it gets, okay?
Okay. So if someone could answer this question between 19 and 22 this semester, that would be a great advance.
What's the obstruction? Maybe that's a bad question.
Go ahead.
Is there an obvious obstruction to this, or it's
Not that I know of.
So like numerical methods will lead to kind of answer? or not?
What's the problem?
A lot of variables.
There's 729 polynomials here. There's 27 times R variables. And so for the R that we're interested in, this is overdetermined. You have more polynomials than variables. Numerical methods like well-constrained systems. But here is an overdetermined system. What that means is any perturbation here, you're going to get no solution. Numerical methods like stability. And so that's the fundamental reason about numerical methods here. Okay, good? So let's move on to numerical methods. How can you use numerical methods to prove that there exists a solution? So prove there exists a solution using numerics. So what I'm looking for here is I'm looking for probably integers.
There's a question.
Oh, go ahead. Sorry.
If you take, say, you can take subset of polynomials here, like of 27 times r. Any
Yes.
subset, will it always give you a solution?
It will, if you take the closure of those, you'll get a solution. I believe so. And so now you have to sort of look and see, okay, I have a subsystem which has a solution, but there could be many points above it. How do I find the one that corresponds to the actual solution of all of these equations? Yes. Okay, so here we're really looking for an integer or a rational solution, so one that we can just plug in. How could we use numerics if we don't have such things that we can evaluate? And so here I'm thinking of my system F, and I'm going to switch, no, I won't switch notation. I'll stick with the same notation. Fn, and here x is x1 through xn. Okay, so I have a well-constrained system, and now I take my favorite point in Cn, and I look at what happens when I do a Newton iteration on it. So what is a Newton iteration? x0 minus the Jacobian of f inverse times f of x0. And now you can take this point, x1, and do a Newton iteration on that and keep going. And so you get a sequence of points. x0, x1, all the way down where xk is equal to the Newton iteration of the previous. Good? So if you know, if the limit as k goes to infinity of xk exists, then this limit is a solution. So if this has a limit, then you know you have a solution. Another nice fact is that if the Jacobian at my solution is invertible, then there is an open set, open neighborhood of X such that for all x0, so open neighborhood U, for all x0 in U, the limit as k goes to infinity, maybe I should call this y.
Sorry. So this statement is if the inverse exists? Is that what you're trying to say?
Yes, if my solution is non-singular. So if my solution here is non-singular, then there's an open neighborhood such that if I pick any point here, Newton's method has to take me back. And not only that, it has to take me back there fast. Yk minus my point x has to be in the quadratic convergence to the k minus 1 y0 minus x. So not only do I have to converge to my solution, I have to converge there very fast, quadratically. Okay? So how do you prove you have such a point? How do you prove you have convergence? So prove quadratic convergence. Via Smales-Alf. For example. The nice thing about this is no knowledge of x, the limit point, is needed, or any other solutions of that. So I can use alpha theory to test just by knowing this point y0. I don't need to know how many solutions, do there exist other solutions. I can test everything locally at my given point. Gregario and I have been discussing, and there's many people in the audience who would like maybe to have some kind of seminar involving alpha theory, numerical solving and things. So if you're interested, we can talk. Very good.
But what about the neighborhood?
Sorry?
But what about the neighborhood? Before
So
you apply the theory, you need to know what is the neighborhood.
So when you apply the theory, you know at this point there exists some ball where there's a solution that lives inside of that ball.
Is the knowledge of how big the ball has to be needed anywhere at any point?
If you know this point, then yes, you can find bounds on the ball. But if you don't know that point, and we're assuming we don't, then we just have some other point. Does it converge? So yes, it's both ways. If you know x, you can get an idea or lower bounds on the size of u. And if you know y0, you can get upper bounds on the distance to the
But
axis.
if you know x, what do you care? You're done, right?
Exactly.
No, sometimes you don't know x. You know the bound.
Right. But if you know x, you're done.
Yeah, but this is more about you guess a y,
Yes.
right? I mean, this is in real life. You're
No, you're not.
You're
Just
guessing
using
why,
good software to get to
and
y.
then you
Exactly.
want to do zooms or guess or.
So take it back to homotopic continuation. We follow our path until we're close to the end, take that as our y0, and prove that it converges. That's sort of one way of using this.
Sorry, can you say your closing? What is this alpha theory that you're using?
So I don't want to go into details today,
Yeah, just a few.
but essentially it's a rules for when Newton's method quadratically converges. And if there's significant interest, I can include that in my talk on Thursday, if that would be of interest to Would you be interested in?
I guess I have no idea what such a rule would look like.
Okay, well,
I don't need to know the details. Just like,
let me tell you. So the first thing is you need to know how far does Newton iteration take you.
If you see my book on
And then the second thing you need to know is
I read Smale. I read Smale. Made sense to me. I checked this one.
how bad are your derivatives? 1 over k minus 1. So this is kind of like a condition number, and this is the distance of Newton's method. And now you take alpha to be the product of those two. And if this number is small enough, 0.15, I forget the magic number, then Newton's method converges quadratically. I've switched from x to y0, I apologize. There you go.
Is this norm specific? Does it depend on the...
That's the 2 norm. This is the 2 norm and this is the operator norm. This is a tensor and this is the operator norm of that.
It requires these things to be in the 2 norm.
Sorry?
It requires the value of alpha to be less than in the 2 norms.
Yes. Yes.
Well, maybe one could add that there is a beautiful upper bound because this gamma is complicated.
Yes.
It involves higher derivatives of all order, but you can upper bound it by a quantity, a condition number essentially, which only involves first order derivatives.
Yes.
It's much nicer.
Yes. There's a nice upper bound, and that's actually what we implemented in Alpha Certified. If you have polynomials, this is a finite maximum, and so you can actually, in theory, compute it. But computing higher derivatives and norms of those is not practical. How much time do I have?
about 15 minutes.
Okay. Good. So, symbolically or exactly, if we can produce the coordinates, then we can just evaluate it and see that it's equal to 0. Numerically, we just have to get close and then rely on some other theory to prove that there is a solution nearby. Okay. There was a quick aside here. I made the assumption that my solution was non-singular. If you look at the system, and this is in your homework, 29 over 16 x cubed minus 2xy, y minus x squared. The solutions of this is only the origin. It's multiplicity 3. And if you take a random point in C2, which is not the origin, the method diverges. And so that's part of your homework problem here. Is be careful when Jacobian is not invertible. You can get some crazy behavior. This is just a nice, simple example of some behavior. Okay, so I leave that one to the homework. What's another way we can think of solving equations? So maybe you want to think of solving means counting. So before I first said, does there exist a solution? And now the next question is, how many solutions are there? So to solve my system means to count the number of solutions to that. Okay? So in the univariate case, we already have the fundamental theorem of algebra, which says that a degree D polynomial has D roots counting multiplicity. What happens in general? Well, in general is quite interesting. The only things that we know of sort of in general are upper bounds. So when we design homotopies, we design the G so that it has an upper bound on the number of solutions. And one simple way to find upper bounds is Bézier's theorem.
Oh, you mean if the number of solutions of G is an upper bound of the number of solutions of F?
Exactly. Yes. Very good. So if f1 through fn, let's go back to algebraic notation, then the set of solutions x such that fi of x equal to 0, phi equal 1 to n. If this and this, then the number of points is bounded by d1 times dn. And what I have to do is be careful. So what can go wrong? Well, it could go that I have infinitely many points in here, and how can I bound to infinitely many points? By this. If let's go to this, where v0 of f1 through fn equals the isolated points in my solution set. So if I ignore all the positive dimensional components and just look at the isolated points, I'm going to have finitely many of them, and a bound on the number of isolated points is the product of degrees. Moreover, my set of solutions are all isolated and bound is sharp on a Zariski open dense subset of polynomials of degree di. What I mean by that is if I take all of these polynomials, in particular fi, to be general in the set of all polynomials of that fixed degree di, then my bound is sharp and all the points are isolated, they're all non-singular, everything is nice. So almost everywhere, Bézou's theorem is sharp. What's the problem? The problem is many of the polynomial systems we want to solve lie on this sort of singular locus. They're not on this Zariski open set. And that's where the challenge comes in. How do we handle sort of this so-called bad set where Bézou's theorem doesn't come? Okay, so let me give you a historical fact or historical example of using Bézou's theorem. And so this is Steiner's problem, I believe 1848. Count the number of conics tangent to 5 given general lines.
Conics.
Conics.
No, 5 given general conics.
Sorry.
It's okay.
Conics in C2. I should look at my notes rather than go off to. Good. Okay. So pick 5 general conics, and now you want to count the number of conics tangent to it. What happens if I pick one conic in this general? Then there's going to be a hypersurface of conics which are tangent to that given one. So there's a hypersurface. There's a hypersurface of conics tangent to the given one. And the degree of it is 6. Good? So now Bézou's theorems, all this question is asking is how many points are in the intersection of these 5 hyperplanes. So I'm intersecting hyperplanes. Hyperplanes are defined by a polynomial, and so I'm just intersecting 5 polynomials. So Steiner said the answer is, and this is why this is infamous, Steiner said Well, I have 6 polynomials, 5 polynomials of degree 6. And so I should expect 7,776 solutions. The problem is this is not correct. And the reason for this is he forgot about the double lines. So this bound, this number, added the double lines in there. And double lines are some family, but we're only interested in the isolated points. And the family of double lines lives in there as a one-dimensional object. And so you have to remove the count for the double lines, and the actual answer is 3264. So just as Newton's theorem, Newton's method, you have to be careful when the Jacobian is not invertible. You have to be careful about Bézou's theorem when you have positive dimensional things that lie in there. They can throw your count off. Good. If you want a nice historical or nice computational, look at Frank's book, which I believe is upstairs in the library for this. You can ask, so this was all over the complex numbers, now you can ask the real question. How many can be real? So of these 3264, how many can be real? And it turns out that all of them can be real. There's a nice construction again in Frank's book that shows this.
Due to Fulton.
Yes, the pictures are.
Who also asked the question.
Fulton asked the question.
Fulton asked that question and he answered it.
Yes. Good.
So maybe may I ask a question? So I wonder what happens geometrically. So you have this if you pick one conic in general position, this defines a hypersurface of conics tangent to the given one.
Yep. And
then you take 5 of those.
Yes.
And you intersect.
Yes.
So you will get 3,264 isolated points plus components of positive dimension.
Yeah, and the components of positive dimension are exactly the double lines.
Okay, what is that?
It's a square of a linear equation.
The square of a linear.
Inside of the space of all conics.
They're tangent for free.
Yeah.
They're tangent for free.
Yeah, exactly.
So it's a P2, it's P2 and P5 embedded.
Okay.
All right, so the last thing, I think I might be running out of time. The last thing for your homework is to look at polynomials like this. 3x plus 4y minus 1, and y squared plus 5x plus 2y minus 3. And by looking at polynomials like this, I sort of hope that you'll be thinking about designing homotopies to solve such a system. So let's look at this here. I have two quadratics, degree 2. So Bézou's theorem says that I have less than or equal to 4 isolated solutions. How many do I actually have? Well, this polynomial system has structure. And one of the structures it has is that the x's only appear linearly. So if I look at what happens, I can rewrite my system in the following way. I have a 2y plus 3, and then 4y minus 1. And then 5 and y squared plus 2y minus 3 times x1 is equal to 0. So because my x's only appear linearly, I can rewrite this as sort of a matrix equation like this. This is a non-zero vector. And whenever I have a non-trivial kernel, that means that this matrix has to be ranked efficient. So this implies that the determinant, so let's call this matrix A, doesn't depend on x, A and y. The determinant of A of y has to be equal to 0, and this is nothing more than the resultant of my system. If I call it, let me just say this is F1 and F2. So this is nothing more than the resultant of that. What's the degree of this polynomial? It's degree 3, and it's univariate. Every polynomial of univariate of degree 3 has 3 solutions, counting multiplicity. It turns out you can show that it's all multiplicity 1. And suppose I have a y that satisfies this. I'm going to get a unique x where this is true. So this turns out that this has 3 solutions. The nice thing about cubic things is you can simply write down the discriminant and you can count the number of real solutions. So part of your homework asks, what's the number of real solutions to this? And you can do that quickly with discriminant. All right? So what is the additional structure of my system here which reduced my count from 4 to 3? And it was the fact that x's only appeared linearly, whereas my original polynomials were quadratic, 2. And so you can generalize this to a multi-homogeneous Béziers theorem and design homotopies based on it. So multi-homogeneous Béziers. And for time constraints, I'm just going to assume the 2 homogeneous case and end here. So assume that, let's say that if my system F is defined, I need 2 variables, x and y, is defined on, pick your favorite space, affine space, product space, or the reverse of them. The count is the same for any one of them. So how many x's are there? There's n x's. How many y's are n y's of them? Then the number of isolated points is less than or equal to. I'll write down the bound, and then I'll tell you all the ingredients. The coefficient of the term alpha n x times beta n y in the polynomial, or in the expression product I equal 1 to nx plus ny of dxi times alpha plus dyi times beta, where fi has by degree dxi dyi. Okay, so that's a long, complicated expression. Let's look at it in this simple case, and then I'll be done for today. So this one is defined on C cross C. Otherwise not known as C2, but I'm going to think of this as C cross C, because that's how I'm going to compactify it as P1 cross P1. Okay, so now look at the degrees. So what is my degree of x in the first equation?
1.
X appears linearly, so the degree in terms of x is 1. And the first equation, y also appears linearly. So that's also 1. So this is a quadratic polynomial that has by degree 1, 1. Let's look at the next one. X's only appear linearly, but y appears quadratically. So it's a quadratic polynomial of type 1, 2. And all this is saying is now take the permanent of this matrix. 1, 2. Take the permanent. Because you have to traverse one x and one y, and the number of ways to make this matrix go through is exactly the permanent, and so this is 2 times 1 plus 1 times 1, which is 3. If you want to use this fancy coefficient expression here, what we're really looking at is what is the coefficient of the cross term alpha times beta in alpha plus beta times alpha plus 2 beta. Coefficient of alpha is 1, coefficient of beta is 1. Coefficient of alpha is 1, coefficient of beta is 2 in the second expression.
What's the definition of alpha and beta?
They're just symbols.
Oh, I see.
They're just symbols.
It's just
Yeah. So all I'm asking is, what is the cross term here? So I need alpha times beta, that gives me 2, and beta times alpha, that gives me a coefficient of 1, and so my cross term is 3. So with that, in the homework, I ask you to find the two homogeneous Bezout count for eigenvalue, computing eigenvalues of a matrix, which is a nice sort of extension of this. All right, I should stop there.
So we have a little more than 10 minutes for questions.
Yeah, we'll go back here.
So earlier on, you talked about like probability 1 of finding a nice homotopy stuff.
Yep.
I mean, are people interested in questions like finding a small set of homotopies, one of which will necessarily work? And so, like, instead of having a probabilistic construction, having some sort of deterministic algorithm potentially slower.
Yeah. So in the homotopy construction, going back to the beginning, f of x times 1 minus t times g of x. Because it's sort of with probability 1, what people do in practice is pick different g's and do the computation, make sure sort of get repeatable results afterwards. So you know that for any particular g, if I set it up with probability 1, it'll work. But now you have to understand that that works over, talking about the Bloom-Schultz-Smale model, that works over that model of computation. However, my computer has finitely many bits in it, and to do the numerical computations. So you use adaptive precision, increase sort of the accuracy that you have, but then also just pick different start systems and rerun the same problem and make sure you get repeatable results.
So I guess I mean, not in practice, because I understand in practice.
Yes.
It's different. But like in theory, can you find just a collection of g's, one of which are...
Yeah, there's going to, what it turns out is there's going to be a whole family of g's that work.
Can you actually pick one? You may be asking.
Oh.
You give a list and one of them will work.
Yes.
That's what you're asking?
Yeah, I believe so.
So you're going to have, what you're going to have is a whole family of them, which all work, and so anyone in this family will. I hope I answered your question.
Maybe.
Okay.
Does this kind of like theory can lead to proof of lower bound for tensor rank? Say, if I give you some tensor which I believe it has rank n cubed over 3, when does it possible that you will give like proof, probabilistic proof that it has actually a rank of n cubed over 3?
If the polynomial system is small enough that you can actually solve it. Yes.
So there exists like polynomial time solution, or
Oh no, not polynomial time.
I thought polynomial time.
No.
But if you exhibit a polynomial evaluated and you get non-zero, then there's no probability at all.
Exactly.
Non-zero is non-zero, so you have a certificate in that case.
Right.
The question is if you get the solution with high probability, when you know the kind of high probability this concrete tensor is has high rank.
That would be nice.
Yes, but you would say that there is no way of solving it in the polynomial time.
No. It would be nice if you could.
I'm sort of changing the subject.
Yeah.
Is there a nice story for the worst case of this problem, for the worst case analysis of algorithms for this problem?
Worst case is you're going to have singularities, and you're going to hit the singularities. And
How about the symbolics?
So let me rephrase what I'm talking about. So there are numerical methods to handle the singularities. but to get provable results about singularities or not. For example, I don't know if Peter will talk about this throughout his talks or someone, you can use alpha theory to certifiably track these paths. And you can prove every step along the way that everything is non-singular, and it's nice. And if the whole path is non-singular, then you get a finite time algorithm to track that path and compute the endpoints. Whereas in practice, so that's in theory, in practice you do different tricks to handle singularities. One interesting question is, suppose I give you a numerical approximation of a singular point. How do I know that there actually is a singular point for that system? Newton's method probably will either converge linearly or diverge, or who knows what happens. So are there different approaches to be able to? You can take the numerics, go back into symbolic expressions, and then sort of use that symbolic expression to prove that there's a singularity there. But it's really trying to find good algorithms for singular cases is really hard. There are heuristics that work pretty well, but if you want provability.
But the symbolic methods do work for, in other words.
Yeah, Grosvenor basis, absolutely.
Right. And is there any concise form of of the worst case?
Doubly exponential.
So it's basically in the number of terms, the degree, and the number, and then.
Yes.
Okay, so it's double exponentially what, in all or
In the degree.
in the degree?
And number of variables. And
I think it's
How about
only
the terms?
single
No, it's
exponential.
polynomial in the degree.
polynomial in the degrry.
I think if you just want to
I
find.
think I made my point.
the geometric.
It's probably not a very well known answer, right? I mean, it's,
I think it's well known. I should ask the complexity.
I think it's only single exponential if you just want to find the solution in geometric way. But however, if you want to understand it algebraically with multiplicities and everything, then it will be double exponential.
Okay.
So the upper bounds.
Yes, Grosvenor basis.
So my doubly
Otherwise, it will be more
exponential
sophisticated.
for singular solutions was correct.
Yeah,
Good.
just a comment. If you want a worst case for homotopy, you need to make concessions. For instance, you should admit that the input is by integers, and the side by integers. The coefficients of the polynomial are integers or rationals or whatever.
okay.
So in that case, it is possible to get results in terms of the, among other things, of the size of those integers, assuming that the system is non-degenerate. So there will be a worst case for non-degenerate systems, and you don't know if your system is degenerate or not at the beginning.
Worst case in general is your computer doesn't work.
Yeah, your computer doesn't terminate. But you can get, usually you can get some
Excellent.
kind of.
I know who to talk to. Okay, thanks.
John, you should point out, when you talk about adaptive precision, you can notice that you're getting closer to singularity.
Absolutely.
With the condition number, and that's really important for the algorithm.
Absolutely. And I hope Peter might say something about this on.
I think I will talk about it in the workshop.
Okay.
And I will talk about different things in the tutorial.
Okay,
More
very good.
basic things.
Very good. So and because I wrote up gamma here, there's this conditioning that gamma handles, and that sort of tells you sort of how many digits do I need to accurately handle my roots there. Conditioning is very important, and I think you're talking, this thing is on conditioning, but also throughout this. Other questions? Yes?
It's just a naive question probably. So Bezout's theorem is giving some kind of worst case number of possible solutions. Is there like a notion of an average case number of solutions for if you're looking at random polynomials or something? Just very curious.
Bezout's theorem is average.
Bezout's theorem is sharp in the average case over the complex numbers.
It's risky if you're
I think
taking general polynomials.
If you are over the complex numbers, it's not a very interesting question because almost surely you will get this number of. However, over the reals, it's a very interesting question. And there are lots of interesting open problems there. So, for instance, there is this very nice result by Schuch and Smale which is kind of an average Bézout theorem, which says that if the equations are chosen at random according to some Gaussian, invariant Gaussian distribution, then the expected number of real solutions is just the square root of the product of the degrees. This is very beautiful. It's exactly the square root. But there are many, many open questions.
And there's a certain type of probability distribution for that. And if you change your probability distribution, you get a different expected number of results.
Is there a good Google keyword?
I didn't hear that.
I was just saying,
Google
is there
keyword.
a good Google keyword so that I can educate myself?
We give you the reference. This is in the book by Bloom, Booker, Supersmail, Complexity and Real Computation.
If I may advertise my book that I wrote with Felipe Cook, the title is Condition, and it's on the shelf. We have there the alpha theory and the gamma theory, and we also have the square root of product of the degrees, so you can find all that.
Very good. So there's a book on the third floor.
And it's not the main focal step, but it's also in there with a slightly different proof than the original.
Yes.
It's me, Implicit, and Felipe Cook.
I mean, I know your guy's name.
Other questions?
Thanks.
So, if there is no other questions, so let's thank the speaker again. The next talk starts at 3:30.
That's why I said
I know, I prepared it.
Danish Almanus was very close to him.
So if there are no solutions, then you have to track all of them.
I had seen the name on.
So my next